Fibroin is an insoluble protein found in the silk produced by a range of insects, including larvae of Bombyx mori, along with species in the Antheraea, Cricula, Samia, and Gonometa genera. Raw silk consists predominantly of two proteins, fibroin, forming the core structural element, and sericin, which acts as a glue-like coating over two fibroin filaments known as brins. Fibroin from the silkworm is composed of three distinct chains, designated as light, heavy, and the glycoprotein P25. The heavy and light chains are connected through a disulfide bond, while P25 attaches to this pair by way of non-covalent interactions, lending stability to the overall assembly. The heavy chain structure is built from repeating sequences of amino acids, mainly glycine and alanine, shaping extensive layers of anti-parallel beta sheets. This sequence, represented as repeated units of glycine, serine, glycine, alanine, allows the beta sheets to pack closely together. The densely packed sheets grant silk its characteristic strength and resilience. These properties enable fibroin to be used across various fields, from biomedical devices to textile production. Fibroin organizes itself in three distinct arrangements referred to as silk I, second, and the third, with silk I forming naturally as it leaves the Bombyx mori's silk glands. Silk decidu represents the organized state of fibroin molecules found in spun silk. This arrangement allows for greater mechanical strength, making it suitable for a wide range of commercial uses. More recently, a structure called silk third has been identified. Silk 3 arises mainly when fibroin is dissolved and located at boundaries such as where air meets water or where water meets oil. Within the fibroin V-sheet, certain amino acid residues found in the N-terminal domain help control when these sheets assemble. Specifically, residues labeled GLU98 and ASP100 carry negative charges at neutral pH, leading to mutual repulsion due to electrostatic forces between similarly charged side chains. This repulsion helps to prevent the V-sheets from forming too soon. However, when the environment shifts to a lower pH, these acidic residues gain protons, and their charges are neutralized, removing the electrostatic hindrance. As a result, hydrogen bonds and interactions driven by water aversion take over, prompting the structure to form the characteristic V-sheets. At neutral pH, residues like glutamic acid at position 98 and aspartic acid at position 100 exist in their deprotonated forms, introducing electrostatic repulsion that disrupts the local stability of the structure. This tension can diminish the likelihood of early V-sheet formation, a phenomenon not limited to those two amino acids, but found throughout the V-sheet forming segment. By creating regions of unfavorable interaction, the electrostatic repulsions delay assembly and help direct V-sheet growth toward its correct structure, supporting the proper assembly of fibroin, a primary protein in silk. The proper structuring of V-sheets is vital to silk's durability, as fibroin forms a foundational element of silk fiber. Although traditionally recognized for its role in textiles, silk fibroin has become highly valued in recent years by researchers in materials science. This attention grew after it was shown that fibroin from the mulberry silkworm could be dissolved in concentrated salt solutions such as calcium chloride or lithium bromide, reverting it into a form similar to that found inside the silkworm before the spinning of silk. This process enables the creation of an array of new materials for diverse applications. Additionally, certain bacteria, including multiple species within the Amycolatopsis and Saccharotrix groups, have demonstrated the ability to break down both silk fibroin and another biopolymer, polylactic acid, contributing to ongoing discussions about material life cycles and biological recycling. Silk fibroin, recognized for its compatibility with biological tissues and its adaptable mechanical qualities, presents potential for use in coronary catheter design when adequate material modifications are introduced. Although fibrin can be processed into both strong fibers and flexible films, coronary catheters demand attributes such as high torque responsiveness, resistance to bending or collapsing, and stability when exposed to blood pressure and flow. These specific structural requirements remain a challenge for unmodified fibroin. Current study directions indicate greater practicality for fibroin as a surface layer or part of a composite arrangement. Here it could offer improved blood compatibility and lower chances of clot formation, without serving as the main structural element. For fibroin to function as the primary material in a catheter, significant advancements would be needed. This effort necessitates controlled molecular engineering, application of crosslinkers, and integration with fibers or other reinforcing materials to build up mechanical endurance and resistance to fatigue and deformation. A manufacturing approach would begin by refining medical-grade fibroin, then combining it with agents that enhance its toughness or flexibility, and with substances that adjust its plastic behavior. The core shaft might be formed by spinning processes that encourage molecular alignment, followed by exposure to agents or treatments that foster stable crystal structures essential for strength. A potential final device may utilize a tube form made up of multiple fibroin-based layers, such as an inner lining for compatibility with blood, a reinforcing braid for structural action, and an outer layer improved for navigation inside vessels. Targeted cross-linking operations would improve the material's resistance to long-term distortion and mechanical breakdown while retaining its ability to conform. Further enhancements could include surface treatments that modify friction properties or discourage clot formation. Each version would need to undergo trials to confirm its ability to withstand mechanical stress, preserve shape under pressure, tolerate sterilization, and remain stable during exposure to bodily fluids. If successfully refined through these advanced processes, fibroin could shift from a naturally derived biomaterial to the backbone of a catheter built from multiple, purposefully integrated layers, with structural performance approaching that of synthetic polymer systems currently in use.